my name is Victor. I work for Dusk network. We are creating a solution that's tokenization of financial assets with privacy in mind. And this is more or less the structure, like a very quick overview over what we do. So it's a privacy blockchain for financial applications. Our stack is built in Rust, mainly. We also have like some Go, but we're planning to migrate to that. And everything is open source, so we made several libraries that are used in the crypto ecosystem, and they are available for you guys to use, to give feedback, to collaborate, or even be part of that. We're also hiring, okay? So the profile we're looking for is Rust developers with WASM experience, but also that's optional, it's not mandatory. So if you have questions about the hiring process, you can contact Emmanuel, he's our director, that's right here. And he'll be available for the chat after, okay? So this is Dusk, and this is basically the hiring page. So basically, you can also contact him via email as well, if you prefer, instead of directly talking to him. I will talk to him because he's here, but it's up to you. So, okay. What I'm going to talk about today is about Rust Unsafe. So before we start to talk about Rust Unsafe, we need to define what's the safe. So safe is a set of the language that follows some rules that will guarantee some properties in the programs developed in Rust that are desirable. So for example, we cannot, under the safe domain of Rust, have null pointers, dangling pointers, or data races, okay? So first question I'm going to ask, who here considers himself very familiar with Rust? Just raise your hand. Okay, so if you have questions, just raise your hand, ask, and this should be very interactive. So, first question. This is actually about the data ownership. So, if you have the data ownership, this encompasses the idea that some data is owned, and this is the safe domain, okay? Is that clear? So, basically, this defines here the set of domain of the safe implementations of the language. So if we're working here in this domain, we don't have some problems that are very common to other languages, such as C++. I think the most critical and famous problem is data races. Everyone here understands what's a data race? Okay, if somebody don't understand, you can just raise your hand and we can go through that, okay? Okay, data race. So basically, you're accessing some data as a mutable reference. So you're going to mutate that data. And you have concurrent references to this data that will also read this value. So if you capture this value and you instantiate it in your local thread or some other concurrency strategy you're using, it may be your data is outdated. If somebody else updates this data, when you are while you are processing the outdated data, okay? So is that more or less clear? So a counter is the most classical example. I have a counter that's incremented by 1 every time I perform some operation. So if I access this counter, the value is 1, and then after some other actor accesses the counter before the first actor increments it, then he's going to receive 1. So it's going to be incremented to 2 and then to 2 when it should be 3. Okay, so this is a data race, okay? The data ownership in Rust states the following. So references, you can have an unlimited number of read-only references to some data, but you can have only one mutable reference to that data, if you're, again, following the safe implementation, okay? And this will guarantee, this is a very simple set of rules, will guarantee us the ability to not have a garbage collection. So what does that mean? Some other languages, such as Golang, they depend on some runtime overheads to drop data after the data is used. So basically, the runtime tries to identify when some data is no longer used, and then it frees the memory, make the resource available for the allocation. In Rust, we do that in compilation time because of these beautiful rules here, okay? So everything clear up to this point? Okay. Now I'm going to start to talk briefly about what's Rust Unsafe. So we have all the guarantees of the compiler. that will provide us the desirable features that will make our programs safe and performant, okay? But sometimes you may want to improve the performance of a program or some particular behavior. For this type of situation, we can use unsafe. So unsafe, basically, you violate some of the constraints of the language, and you are basically stating to the compiler, okay, I know what I'm doing, just let this compile. We're gonna be more flexible with some rules, but everything's gonna be fine, okay? So with unsafe, you can dereference raw pointers. I'm gonna talk a little bit more about this later. And of course, you can call other implementations of unsafe functions and traits. You can mutate static values. So, and also, there is an implementation of unions in Rust. It's not really broadly used, but sometimes there's some particular use case. And I put the definition here just to make it clear, because it's also part of the unsafe set. But again, it's not super used. So basically, a union is a data structure that overlaps the attributes. So that it's not relevant. So anyway, that's it. Very important thing. Unsafe domain will not disable the barrel checker, okay? So we have a lot of misconception that you can violate these rules. No, you cannot. What you can, however, is to use the reference of raw pointers and manually disable that. But this is not explicit. So the barrel checker still exists for unsafe, okay? So any questions for this part?
One, would you say that Rust unsafe is sort of a language apart, or is an extension to the Rust safe, or how should I look at that?
You can see this as an extension, yes. So basically, you have the safe domain, and you have the unsafe domain. The unsafe domain is some functions that are defined as unsafe that you cannot call from the safe domain. So they're complementary, you see? So it's an extension, yes. Any other question? No. So the question was, if using safe over unsafe imposes some compile time cost, the answer is no, because all of this is going to be translated to the intermediate representation, and then from there we perform the optimizations. So, of course, depends on how you implement. So if you call less functions with the unsafe, which is very often the case, then yes, but it's not direct. It's not because of the unsafe. It's because of how you create your program. Okay? So let's skip on down to the next one. So, okay, you asked. You have you have the safe Rust that will provide you a lot of interesting features, and you can do whatever you want. So the lemma of Rust is hack without fear. So basically, you can do anything, and you're gonna end up with some nice software that's reliable, performant. So why would you go beyond that? Because you want performance, most of the time. So this is the root reason why we use unsafe, except for FFIs and some more complicated things. But the main reason usually people go for unsafe is to increase performance, okay? And I put this Sonic that was a very famous meme on the internet, so some of you may recognize that, okay? So, okay, before I proceed, there is a honor mention to Rust Belt. This is an academic project. They are trying to prove that if you use unsafe, complying with certain formal verifications, with certain rules, your code is actually safe, okay? So what they're doing is amazing. I put here the link so you can get the slides later and check the resources. So basically, what they're trying to propose, I will not be brave enough to say that they already proposed, but they're very advanced, is that guarded unsafe code encapsulated by safe code is per definition safe. Okay, this is not trivial, absolutely. And they create a system that will allow you to declare some unsafe code as safe, okay? This is their proposition. This is the most relevant paper for this talk that they produced, so it's a thesis. You can also check the link. And here they're describing the evolution of Rust language, and this problem of unsafe code and some other situations. So it's very nice resource, so if you guys are curious, take a look into that, okay? Anyone was familiar with Rust Belt here? Yeah, okay, so go for that. By the way, they are on the academy field, okay? So they have open positions for PhD. I don't know if somebody is into that, but these are nice guys. Yes, Germany. Yeah, like they're associated with a German university, but I'm not sure actually, like what's exactly the university. Yeah.
How does unsafe code perform better?
Yeah, we're gonna get there. It's not necessarily true, okay? So, but we're gonna get there. He asked why unsafe code performs better, okay? So this naturally depends on how you implement that. But the idea of unsafe is to provide more tools to do more stuff. So basically, you skip some of the rules, and then you are more flexible to optimize the code according to your specification. So this is the idea. It's not that unsafe per se will make the code faster. This is not true. So okay, we're gonna just go through like some common definitions that I'm gonna use like in this talk. So we're gonna be on the same page. So okay, type soundness is a concept in computer science that says that some type representation behaves according to some expected properties. Okay, so the expected properties of Rust is that you're not gonna have memory leaks, you're not gonna have data races, and so on. So we have the expected set of features of the language that will be guaranteed by default if you use safe code, and this is the Rust type soundness. Unsafe, okay, as Emmanuel asked, it's a set of code or interfaces whose memory cannot be verified by the type system. So basically, we kind of violate the Rust type soundness, or we guarantee that by ourselves. So this is the preferable scenario. So if you're ever going to use unsafe code, you need to keep the rules that makes the type sound, that are very well listed in the documentation, but implement this on a manner that you will not violate them. So you need to just be aware of that. Undefined behavior. So this is a very famous thing, like for other languages too. So basically, you have a language specification for all the languages, like C++, Java, Rust, or whatever. In the case of Rust, undefined behavior is that when the execution of a program will not comply with the language specification. So the language specification is related to the rules I mentioned. And whenever you have UB, how we short this up, it's very often related to some unsafe code, okay? So if you use only safe, unless there is a bug in the language or some very critical problem, you're not going to face undefined behavior. So if you use safe code, for example, you can compile for different architectures, and your code is virtually guaranteed to work. If you don't follow that, you may face some undefined behavior if you don't plan very well what you're doing. Okay, and also deferenceable. So this is the idea that you have a pointer, okay, and this can be safely deferenced to some allocated object, okay? So I put here a quite long description. So basically, there is the memory space for a data object that you allocate, and this pointer, long story short, points to some valid position of this reference, okay? So basically, this pointer can be safely deferenced. Is it more or less clear? So if you point like to something outside or something out of bounds or unaligned, we're not going to go into details of that, but this is going to be a violation to this rule. And a taboo, this is basically the idea of this talk, is not something related to Rust. It's something related to society. So as you can see, an implicit prohibition of something based on a cultural sense that it's too sacred for ordinary people. So first of all, we're not ordinary because we're Rust developers. And second, there is a kind of taboo with unsafe Rust, okay? So this is the definition of the Britannica Encyclopedia. I didn't invent anything of that. So, but the point is, like, there is a taboo. So whenever people mention, I'm going to use unsafe code, some people are scared, some people are like very resistant to that. We obviously should not be like that. Like we should be open to discuss. So there was a not so recent incident with Actix. So they were pro unsafe, and there was a huge fight in the community. So this is a symptom that we have a taboo. Any questions here? Okay, so Rust. Rust is beautiful because you see the function signature. You understand what the function will do, okay? So I will propose an exercise for us together to read this function signature, okay? So basically, like pointers, they're used mostly for unsafe code. Okay, that can also be used as safe, but you very frequently encounter like them as unsafe because the references, when you don't want to manipulate some unsafe code, are pretty much enough to do more or less everything like that you would like to do. So first, this is like the method of a pointer. It's the asref, and as you can see, the syntax is declared as unsafe. So this belongs to the unsafe set of the language. It will consume self as owned and return an option to a reference of t. So I would like somebody here to try to define what's happening here just based on the function signature. Yeah? Okay, I can also do that, but please. Precisely, and why an option? And why an option, and that's not just the reference? Precisely. So just repeat for the recording. So how he defined? It's giving an option to a reference to some owned data by someone. We don't know who that is. And it's an option because you don't have a guarantee that this data is still there if this pointer is valid. In other words, if this pointer follows the rules of safe Rust. So basically here I listed the properties in the documentation that we want to guarantee whenever you use the safe function. So if you check the documentation of the standard library, you're going to see that the pointer must be properly aligned. So going very fast on that, like some targets, some architectures, they depend the pointer, the address of the pointer is divisible by a constant. If it's not, you cause undefined behavior, okay? So this is to guarantee like interoperability with different platforms that you might compile your code. The referenceable is the thing we defined before. So basically, you need to point to some valid data, as you mentioned. And yes, so basically, it must be initialized. So what's the meaning of that? So you have your memory space for the execution of your program. If you don't initialize a memory and you put a pointer there, you may attempt to free that code if you take ownership. So a lot of bad stuff can happen. So if you guarantee that whatever you're referencing this pointer to is initialized, then you are good to go. So if you comply with these rules, you can use this function. Basically that. It's not so simple, however, because a pointer, as most of us probably know, is just a number. Like we have a number that's an address in memory. And you can just construct a wrong number if you don't derive this from a precompiled reference. So the compiler will calculate all these things for you, but in this case, you're deciding to calculate by yourself. So for some reason, you think it's optimal to do like that, or you want to have like some particular use case, but you want to manage this yourself. So you can use this function. So here I put a very quick example on one possible usage of the asref of a pointer that's unsafe, and we actually create a reference to some data that's considered safe by the compiler, okay? So here we declare a pointer, so let pointer equals a pointer to a byte, and it takes this reference to this 10, that's a constant value, declared as a byte, declared as a pointer of U8. All clear in this line? Then after, I transform this pointer into this variable that I call asref unchecked, okay? So it's a very common standard in Rust that we use this unchecked suffix whenever we want to say, hey, I don't know if this data is there, I don't know anything. Just take it and do whatever you want. So it's basically doing that. So I take this pointer to this static 10. This is a constant, so this is safe. And I transform this into another reference to the same data that I previously knew it was there because it's on the static space. Any questions here? So yeah, I hope it's not too confusing, but just recapping. We comply with the rules, the function is safe. Long story short. And these rules are specified in the documentation, okay? If you go to the function, to the model of the pointer, you're going to see all of that I have here. Another usage for the unsafe code is if you want to write directly ASM. Okay, I put a very simple code here. Like it's not really doing anything, it's just moving 5 to a register and asserting this is 5. Just to show like a potential usage for that, okay? However, ASM you're gonna use unless, only if you have like some very, very specific usage. So like we have a very good support for the intrinsics in Rust. So for example, if you compile some code to the native CPU, the compiler is going to perform some very good optimizations for you, and it's very hard to beat the compiler. So unless you really know what you're doing here, like you have like some very specific instruction sets, you have like some very specific hardware you're going to execute this application in, it's generally preferable to allow the compiler to perform the optimizations for you, and they're usually in the intrinsics model. So if you go there, you'll see like a lot of AVX functions, a lot of other very nice functionalities available for you, but they are restricted to some platforms. So some are supported only by Intel, some only by ARM, and so on. So, okay, supposing you have some use case to use ASM because you designed your own CPU, you have your own instruction set, so you decide to do like that. It's possible to do, but you can only do that in Unsafe, okay? So here is a very simple code. So any questions here? Yeah, it's a very simple example. I move 5 to x and I assert x equals 5, okay? Another use case for the Unsafe is with FFI. So we have like, for example, the libsodium. It's a very famous cryptographic implementation in C++. Okay, they are very mature. Like they have a very strong community backing them up, and they have a lot of tests. They have a lot of people review that code. So you don't really want to re-implement that, unless of course you have all these resources they had available to you. So like sometimes people take implementations in other languages and they transpose this to Rust, okay? Who here is familiar with FFI, this foreign functional interface? Yeah, so this is what it is. So if you want to take a look what that is, you can check this repo. It's a Rust FFI to libsodium, okay? And recapping the idea is we're just going to take profit of the very mature implementation we have for C++ and make it available in Rust, like natively. But you can only do FFI through Unsafe, okay? So here also I put a very small snippet on how would be a FFI declaration. And you need to use probably libc, or I don't know, depends on your FFI, of course. And you see, like, it's not very readable, actually. Like this, you're transposing the implementation of some other language to Rust. So you have all these directives here declared, and they're important. So basically, here I just set the environment variable A. So I take like n and v, two constants, two pointers to some bytes, and I return this cint from the libc. Libc is the libc implementation in Rust, and so I'm returning an integer on this. So if you use that knowledge we just discussed previously, like when we're checking the function asref for the pointer, you cannot really understand what's happening here. Like this function is not this. There's no clear description at all in the signature per se. So you would like to avoid that if it's possible. But in the case of this implementation sold you outside, there was no point in avoiding that. So basically, they just provide some good documentation on how to use their functions and some good interface for the Rust users to call their functions. So they will not expose this type of stuff. They will create an interface in front of that. And of course, the compiler will optimize all of this. So you have like a kind of zero-cost abstraction. So when you call this function, that's implemented in C++, in libsodium, the optimization of the compiler will treat this as a native code. Everything is LLVM, but I will not extend too much on this part. So this part here is clear. Like first, FFI. We have an implementation in some other language. We can call from Rust. Second, it's not very friendly, so you need to put something in front of that. You cannot just expose this to the user because he has no clue on what's happening. And it's actually not very compliant with the ecosystem we have in Rust. So if you guys want to take a look, here is the C implementation. And here is the Rust implementation that's available on Crates.io as well. Okay. Okay. We have like some other parts of Unsafe as well. So one example is the Transmute. Okay. So I put this alchemist, like this very shady image with a lot of black magic and demons, because this is evil. Okay. Very simple. So if you're using Transmute, probably, very probably, you're doing something wrong. So yes, we have this taboo that Unsafe may imply that you're misusing like Rust. Transmute, this is kind of true. So let's try to read the first item. So somebody wants to give a guess what's the meaning of this first function? From the signature. Go. I don't know. Precisely. So you define like some static types here, t and u, and you take as argument t and you return u. So basically you say, okay, there is this statically defined type that we follow all the rules of soundness, everything that Rust provides, and we're saying, okay, it's not this type we're working with, it's this other type. So yeah, of course, you probably know what you're doing if you're using that, but this is serves for a lot of undefined behavior in different platforms. And now, somebody wants to try to define what's the second function? Somebody else wants to give a shot? Yes, yes, it's true. Yeah, yeah, that's true. So yes,
actually borrow, so
exactly.
will not stay.
Precisely. So we take a reference to t, okay? We copy this data to some new owned value, and we transmute that value, okay? So this is even worse than the transmute, actually. Because you don't know if they have the same memory representation, the same size, if it's, you don't know anything. You're just saying, okay, take these bytes here, copy somewhere else, and declare this as u. This is what you're doing here. So with this two, I would be very careful. So like, I actually don't know a use case for them that's justifiable. So if somebody wants to talk about one situation they had to use transmute, and this was really nice, it would be super welcome, because I never did. Okay, so do what, sir? Yeah, so you have the pixel representation as a sequence of bits, and you want to transpose this to just bytes, yes? But this is for serialization purposes. But if you use, for example, the pointer to the first position of the pixel and then use as ref instead. Yeah, like most of the cases, I think you have like some workaround to not use transmute. I know, this is how I see, but the transmute for me is this black magic thing. You also mentioned the use case, right?
So many byte arrays everywhere, and you know that we actually store some structure. It's what we use cast in C or C++ form. You can know there is something, and you transform it from forth and back. And outside of FFI, it may be used for unions and for some optimizations of absence, but again, it will integrate.
Yeah. Yeah, like as long as you take a lot of care. So just to repeat on the mic the definition I gave. So for FFI, you have like some type declared that's just seen as a set of bytes in Rust, and you need to convert this representation to some concrete static type in Rust. Yes, that's true, and maybe there is not even a workaround for that. So for FFI, it's applicable. But again, he mentioned also that you need to take a lot of care to not get shot on your own leg when using that. Because you need to declare your static type as a C memory representation if you do that. So if you don't do that, like a lot of not nice stuff can happen as well. So basically it's like, okay, if you need to use this guy, use but take care. And it's a very good practice when you're using these dangerous functions to put very big blocks of comment in your code to describe, like, okay, I'm using this unsafe code. Why I'm using that? Why this is safe? If you cannot answer why this is safe, don't use it, okay? Do the expansive way and that's it. So answering your question, for example, like here, we have some type defined in IFFI, and why this will be more performant than just, I don't know, trying to translate this to a static Rust type. Because you have the same memory representation that you, according to your specification, know that's the same memory representation in Rust. So you can just make a reference to this set of bytes and declare this as your type, as your own data, instead of copying this somewhere else, parsing or running like some decoding, some additional overhead, some runtime overhead that will impact your performance. So this is a shortcut, basically. You tell, okay, this pointer here contains this data, and that's it. Don't do anything else. So you reduce like a full set of decoding instructions into a single function, and this way you gain performance. So it's not directive. It's not because of the unsafe. It's because of what the unsafe allows you to do. Okay, so also like there is a lot of relevant and connected things regarding this topic. So it's interesting to take a look. So we have like some very good references in C++ as well. And memory ordering is a super critical subject when we're discussing this type of stuff. So you guys could just take a look on the C++ documentation for that. It's basically a very chaotic thing on how the data access to some particular segment is prioritized by the machine, by the host you have, like by the CPU. So you can check the documentation of Rust. They have a lot of interesting information there on how the ordering is done. So this is used to implement some very low-level stuff, such as mutexes and some other structure. And also the C++ reference will provide a lot of very nice information. So if you're interested in the subject, you should read all the stuff that's there. There is also the very famous Rustanomicon. Raise your hand who knows that. Yeah, and the more hands I see this time. So this, take a look. Take a look. Like if you never checked that, please do. So here they compile a lot of interesting cases that you can implement with Unsafe, and they clarify a lot of the Unsafe usage. So it's called The Dark Arts of Unsafe Rust. So I don't know who here is a fan of H.P. Lovecraft. It's obviously inspired on the Necronomicon. And they created this Rustanomicon thing. So yeah, the idea is they want to centralize the documentation and make available a lot of use cases you can kind of copy and paste from here to your code. And you have the community backing you up. So if you want to use some Unsafe, you're not so sure, you can take a look there. And if it's there, the likeliness of this being like a safe code in a sort of way is high. And like the last reference is about this talk. So I was very happy when I saw that. Basically, she described how she wrote this GilBDT library. Long story short, it's a matrix, basically. It's some data structure that's matrix-like. I will not get into details about that. And how she optimized that to be super fast. And she used Unsafe. I was very happy to see this on the Rust conference because of the taboo thing. So yes, she described why she used Unsafe and how. So what was her scenario? She has some data structure that per definition of the data structure, will have the algorithm's implementation guaranteed to be safe because all the internal references, like to search data, to insert data, to update indexes, will always point to some valid position of the table. If, of course, the data structure is implemented correctly. So what she had? Initially, with the raw Rust implementation just safe, she was copying like values because, okay, she knows that some pointer to some part of her data structure is guaranteed by the algorithm to point to some non-dangling pointers, non-null initialized data, everything like very consistent. In other words, the set of rules we defined before, they are guaranteed by the data structure. So she knows that. So she can use like she can cast pointers to references safely. This is a very interesting talk. She describes this problem very briefly. I recommend you all to watch that. And she also mentions like some other tooling, like to find like some possible optimizations in the code. It's a very nice talk, okay? So these are the relevant topics. Any questions about any of these three? That's it. The next one. So yeah, that was the talk. Any questions like overall regarding, or maybe you want to share one experience you had with Unsafe? Just go for it.
I have a question.
Mm-hmm.
It is about Transmute.
Mm-hmm.
Is it recently we saw the rise of zero copy serialization libraries that are we also one and we also sponsor. That essentially is something that allows for a transformation of type.
Yeah.
Do you know they use Transmute there to accomplish this goal, or they accomplish it in some other way?
Well, I need to see their implementation. I don't know what they're using. Possibly, yes, because looks like that. So they have one type and they want to translate to the other, so looks like Transmute. The point is, whenever you use Transmute, so you need to be super careful. If they're super careful, then it's fine. But I didn't see the code, so I don't know if they're using that. You also raised the hand, right?
Yes. I have more than all that is small remarks that Transmute actually does check the size of the structure to try to transmute something as different sizes and will fail at compile time. And also a small remark on the sodium. You actually mentioned different times that it's C++ or C. It's actually C specifically.
I see, yes, okay. Yeah. It's C, yes?
Yes.
Yeah, maybe. Yeah.
It's from C. But I think the main thing I'm not sure how they phrase it, but I think it's an alternative point, at least that I also checked the Rust book, sees that Unsafe is not really about gaining performance, at least what they say, but it's a little more like you can't prove certain things sometimes. Like it's like basically the compiler can only possibly be taught like so many things, and sometimes you just cannot express something that you can know manually in a way that Rust compiler would be able to assume. So so this is like a popular case of that just teach compiler that hey, like I know you can't understand that this is safe just because of semantics, but I manually verified it and making marking it trust forward. This is kind of the vibe how you do it. And I think sometimes I cannot also use for performance, but this is not like kind of number one topic. That's the book. But that's just for a content point like go through some extent.
Yeah, this is a matter of perspective. So, like, I think the following statement holds true. Any implementation having Unsafe, you can implement in safe. You just need to copy more. Right? Yeah, I don't know. You need to do more expensive stuff. Like, yeah. Yeah, no, but yeah. Precisely. So if we go for the ASM section, yes, this is a whole new universe. So if you're using some very specific platform host, then yes, you need to go Unsafe because Rust has no clue about what you're doing. So this is one example. Like this is not about performance. This is about like the only possible way to implement the whole thing. Like, however, like the common use cases fall into this. So Okay, if you want to over-optimize, you can use intrinsics instead of explicit ASM, unless you have a very strong reason to do so. It may be the case sometimes, but yeah, it's super particular. So yeah, but as for the use cases for unsafe, I'm trying to think of one that you cannot implement in safe. That's not very specific hardware. It's just like some Intel architecture thing. I don't think there is one, actually. I cannot think of one. Maybe. Yeah, but if you copy this and you declare this as a new type, it's going to work, right? Yeah, that's a point, yes. Yes, it's more expensive, yes. But that's a point. You can implement this as safe. It's just a matter of optimizing and saying, okay, trust me, compiler, this is good. We're good to go. So yeah, this is a matter of perspective, of course. This is a general rule, of course. So we have exceptions as for everything in life. I think the strongest one is this guy here, very specific architectures.
Also, it's used in elections. Sometimes you just cannot. I don't remember the exact count, but there were two where it's just specific how you iterate. You kind of illegal according to Rust, like two things to do. For example, you're in a loop or something that, and you kind of just know as a programmer that this is safe and I'm not sure. Maybe to some extent also unwinds in the end performance, but basically at least this is not like always. It's not like always Rust like normal Rust code. It's slow. It's more like at least if I understand the vibe.
Yeah.
It's more like sometimes you just cannot do things or you cannot do efficient and you just kind of work around that. But by default, they actually try to make zero cost extraction. So by default, they try to make a way that safe is actually as fast and only rare.
Yeah, that's true. The general direction of the community is if you have a use case that cannot be implemented in safe, this should be incorporated into the standard library, okay? So this is, I don't know if we can open a browser here to check the ping documentation for future. Yeah, kind of. So if we take a look into that, this is one example. We have async. It's quite recent. I don't know, 2 years, 3 years, whatever. What's it? Ping. Yeah.
Pin.
Yeah, pin.
Pin, P-I-N.
Yeah.
Yeah, pin, like
So if we can put on the screen, it's going to be very nice.
very important to see.
Yeah, it's actually mandatory. You cannot do the thing without that. So, and they incorporated this into the standard library. After very long discussion, they decided, okay, let's bring this guy here. It was part of one crate, and they just incorporated because this is a use case they could not implement in safe code, but they're all the time with these efforts. Okay, I cannot do this. This makes sense. Obviously, it needs to make sense in a general perspective, not only for a very specific use case. Then you bring this to the library, and then you can use this as safe. So yes, maybe there's some hidden cases out there in the wild, but ideally, yeah, is it okay? Ping. So what this says, okay? You have some data in memory, and this is not gonna move. Okay? It's gonna stay on that position. You can cast pointers to that. You can do whatever you want. The data is not gonna move because sometimes at runtime, depending on the operating system, the compiler, the architecture, a lot of things, your data can move. I'll not overextend on that, but this is basically how it works. And with this, you're telling the compiler this should not move. And with this, you can implement the reactors and everything. So for you who are curious, check this model. The documentation is awesome. Also because it was a very big discussion in the community to bring this to the standard library. So the result of the very big discussion is a lot of documentation that's very interesting. So they're saying here, okay, why ping is needed? what it's bringing to the language. And right now it's used mainly for async, but they may have like some implementations out there using for some other stuff. I'm just not aware of them. I think it's only for async, but it's possible. Why not? Like you can have a pin data for some, I don't know, graphs implementation. Why not? Yeah. So this is a very good example that resembles. So recapping, they bring to the standard library these cases. So if we find a new one, the good thing about Rust is it's open source and it's community driven. So we report the problem, we discuss there. Maybe the discussion will be a little bit too long, but this is good because, yes, everything will be understood and covered. And if it makes sense, it's going to be integrated into the standard library. Cool? Anything else? Yeah, precisely. And that's the case of the talk of the girl. So she's guaranteed to have bounds checked with her algorithms. So she said, OK, I'm using Unsafe. That's it. Yeah, precisely. So yeah, exactly. So like, OK, so supposing you are a little bit aware of what you're doing, but you're not totally aware. Don't use Unsafe. That's it. Very simple. But if you're sure of what you're doing, you can use that, and it's amazing. You have a lot of interesting possibilities. And it's interesting also to play around with that. So if you check the Rust Nomicon, they have a lot of small little games there that you can implement by yourself, and you understand like in detail how this thing works. Cool?
Interesting. It's also used by archive.
Oh, that's it. There is another use case for ping. Good.
And I believe it is because when it's stored, when types are serialized using the trade system Rust, when they are stored on also on disk, then during the deserialization, then it basically to have a constant location of memory to deserialize from. So it needs to guarantee that the data remains the same location. It's not going to. That is.
But this is to guarantee no copy or for something else? Just to guarantee. Yeah. So performance. So is that?
You were saying that.
Yeah.
That you weren't aware of another YouTube.
Yeah.
Outside of async.
Yeah, this is interesting. There's this library. It's called Archive. So okay, I know more or less the concept. Maybe Emma wants to elaborate more about that.
It's basically a serialization. We use it because we have some requirements for performance. We have a lot of different programs that are running on WebAssembly, and they need to access the host system in order to do very high-performance cryptographic operations that otherwise WebAssembly wouldn't allow. And this very high-performance operation, basically they need FFI. Now, in order to maintain the type system inside of WASM, because we need to know the types of, in order to perform cryptographic operations, then the data needs to be serialized from WebAssembly, written by third-party smart contract developers. Smart contracts are decentralized programs, essentially. So they need to use some types, and this type need to live simultaneously on WebAssembly and on the host in order to basically perform this operation. In order to make it transparent to the developers, whatever is happening on host, then essentially this type gets used on the host in a clearly transparent manner from the developer. And of course, you need to serialize from WASM into the host, perform the operation, have a result, and then serialize it so you get your result with WebAssembly. This was a huge bottleneck for us because any time that some deserialization happens with memory movement, this cost has got cost essentially. So doing zero copy serialization is extremely cheap, both from performance perspective and also for the perspective of using this program, paying for this program, paying for gas by the technical blockchain mumbo jumbo. So it's zero copy serialization. Serialization is something that is quite that we started recently to solve the problem, and so it doesn't use Transmute.
Yeah, like ping is super powerful. Like it was incorporated into the library because it will allow a lot of cool stuff like this. So just to be on the same page, a zero copy serialization is basically you have the memory representation of some set of bytes, and they're going to be translated to some other type without performing memory copy. Okay, that's it. It's super simple. The name explains by itself, but I'm just like giving the concept. So yeah, yeah, cool. So and we have Unsafe also for ping, as you can see. Let me find the documentation there. Just. Yeah. Okay. Oh my god. Okay. It's the get, check, and mute. So like this is unsafe. Okay. So basically, whenever you see unchecked, it means okay, you know what you're doing. Do it, and it's usually unsafe. Okay. So I don't remember if there is a function in the standard library that's unchecked and it's not unsafe. Maybe there is, but it could be like an exception. Yeah, it's super long. I don't really like that as well, but it's kind of legacy now because everything is unchecked. So I always like very short name for functions, but this is like a subject for eternal discussion between developers. So some think you should describe the name like using all the words in the dictionary, and the others like me think you should use very short words. So that depends. And yes, unchecked is quite a long one. Cool, so that's it.